highlighted the 0 line. So these are cumulative time series. So what it shows is basically, imagine a layer of water averaged over the glacier that's removed or added to the glacier through time. So this one goes from 0 to -30. So South Cascade Glacier in Washington has the biggest loss of volume or mass since the program started in the 1950s. Its whole surface, if you average the change over the entire surface, it's about 30 meters of surface elevation change due to the mass loss from that glacier. Golcana Glacier is a bit further north. It's cooler up here, so we've lost less mass. But both the continental climate glaciers have this steadily decreasing negative trend. There hasn't been much of a recovery since the program started. They've just been dwindling. The coastal glacier, Wolverine Glacier, has more up and down. And that's because of the high rates of precip on the coast. There's more variability in the precipitation. The summers are cooler along the coast, and so the glaciers are more influenced by wintertime snow than they are summertime rain. So there's more variability in that, but all three of these time series show pretty dramatic changes since the early 1990s. There are no real recovery periods anymore, and the rate of mass loss is increasing. So then we can take what we have here in North America and compare it to what the world has. So there's a great organization, the World Glacier Monitoring Service, and they take all of the glacier mass balance data, the field measurements. We can do this from photography, and as I'll show you, we can now start to do it from space. And they try and integrate these records together and come up with global estimates of what's happening to the glaciers. So the red triangles are places where we have more than 30 data points for a single glacier. So there's not very many. There's actually 30 that have 30 or more measurements worldwide. Antarctica, 1 over Greenland, and 1 over Alaska. So again, we have the fastest changing glaciers and we matter. And we're not studying them all that well. So let's take these new spaceborne measurements and look at what they're telling us about the glaciers. So this is a new kind of figure that's been popularized for a while. And so I'm going to show one for the mountain glaciers, one for Greenland, one for Alaska, and talk about what they mean. But the width of the box is the interval over which the measurements were made. So this one goes 1950 to 2010. Some of those ones that say Alaska on them are big and long, so they're long interval measurements of mass change. And then the height of the box tells you the uncertainty in the measurements. So what you can see several things from this plot. First, not every region is represented here. We don't have a change estimate for every region of mountain glaciers. The next thing is that Alaska dominates. All of these boxes down low are Alaska's signal. The ones up above are the Russian Arctic, Svalbard and Iceland, Canadian Arctic. There's less ice in a lot of those places, so the overall magnitude is lower than we have a lot of ice up here in Alaska. And then the third thing is that if you fit a curve through that with your eye, you can come up with a very similar shape as the curves from Wolverine and Golcana, this increasing rate of mass loss. So here's two from the two ice sheets. Greenland is on the top, and Antarctica is on the bottom. For Greenland and for the West Antarctic ice sheet, you could fit that same shape curve through the boxes. East Antarctica is actually gaining mass right now because it's warming up there. We're getting more snow in East Antarctica. It's not balancing the increased rate of mass loss from the West Antarctic ice sheet. One of the things that I want to point out is that these curves only go back to the early 1990s. It was around 2000 where glaciologists finally had the confidence to stand up and say the sign of the mass balance of the ice sheet is negative or positive. Before that, we had no idea whether they were gaining mass or losing mass. It's only since we've had spaceborne measurements that we can have the confidence to say that. Now we have pretty good confidence that the ice sheets are losing mass at accelerating rates. And the scale of these mass changes for either ice sheet is an order of magnitude, or factor of 2 even, similar, and they're about the same size as the mass losses from the ice sheets.